So at this point now, we can go back to ridge regression, and just like with least squares, we could relate it to maximum likelihood. We can now relate ridge regression to a probability distribution. And so this is something called maximum a posteriori. So remember, with the likelihood model for linear regression, we modeled data pairs xi and yi using this linear model. And we saw that if we put the values yi into an n-dimensional vector y, and we stack the vectors xi along the rows of a matrix capital X, that the least square solution, which is the value of w that minimizes the sum of squared errors, which is what this is equal to, was equivalent to the maximum likelihood solution for this model, where we assume that y is generated from a multivariate Gaussian with mean equal to xw and covariance equal to sigma squared I. So these two problems share exactly the same solution, and so we can view the least square solution probabilistically as being a maximum likelihood solution for this model on the data vector y. So the question now is whether we can make a similar probabilistic connection for the ridge regression problem. So I'm going to step through that process. First, what I'm going to do is I'm going to make an assumption of a prior model for the vector w. So we see that the likelihood model is, again, that y is generated from a multivariate Gaussian like this. We'll make this hypothesis. And so what about a prior on w? Let's hypothesize a prior distribution on w. And let's assume that the prior on the vector w is Gaussian with mean 0 and covariance equal to lambda inverse I, where this is now a d-dimensional multivariate Gaussian if w is d dimensions. Then we can write the prior density of w in this way. So this is simply the density function that corresponds to this probability distribution. And now let's think about trying to find a value for the vector w that satisfies at the same time, and this is vague, but it'll become more concrete in a minute, that satisfies both the data likelihood, this term, and also our prior condition or our prior belief on the vector w. So this leads to something called maximum a posterior estimation. So the maximum a posterior solution, or MAP solution, seeks to find the value for the vector w that is the most probable under the posterior distribution. So what we say is that the MAP solution for w is equal to the argmax over w of the log of the posterior distribution of w given y and given x. And so again, because the log function is monotonic, the value of w that maximizes this posterior is also equal to the value of w that maximizes the log of that posterior. And so we work with the log out of convenience. And so the first step in trying to find this thing, this value for the vector w, is to use Bayes' rule. So we take the posterior of w and we replace it with Bayes' rule, which we know to be this. So this distribution is equal to this distribution. And then, using the fact that the log of a product of things is equal to the sum of the logs of those individual things, we can say that the log of this product is equal to the log of the likelihood plus the log of the prior minus the log of the normalizing constant, or the evidence term, or the marginal likelihood of y given x. So this is what we ultimately want to maximize over w. And so let's contrast this with maximum likelihood, which simply tries to find the value of the vector w that maximizes the log of this likelihood. Now we've added two terms. We've added the log of the prior, and we've added this additional term, which we observe doesn't actually involve w. So no matter what this value is, changing w is not going to change this value. So since we're not interested in the value of the maximum, we're only interested in the location of the vector w that maximizes it, meaning the argmax, we can eliminate this term. We don't even need to look at what this term is, which is useful because that means that we don't have to calculate this integral to find this term. And in many models, that's going to help solve a problem where we actually can't calculate this integral in closed form. Okay, so let's look at the map solution for the linear regression problem that we're discussing. So again, the map solution is equal to the value of the vector w that maximizes the log of the likelihood plus the log of the prior on w. And because we've assumed a Gaussian likelihood, we can replace this term with this term, where we've again removed the constants that don't impact the solution. And also, the log of the prior, which we've assumed to be Gaussian, now is equal to this term. And again, we've removed some constants that don't impact the solution. So let's call this objective function L, and then try to maximize this objective over w. And so again, how do we do this? We take L, we find the gradient of L, and then we find the location of L. We find the location w at which this gradient is equal to 0. So we take the gradient of L, it's equal to this, and we find the value of the vector w such that this vector is equal to a vector of zeros. And using simple algebra, we can find that the map solution, therefore, is equal to this, which we recognize as being the ridge regression solution, where we've simply redefined the original lambda term to now be lambda times sigma squared. So notice that just like least squares, the least square solution maximizes the likelihood, so it corresponds to the the maximum likelihood solution. Ridge regression maximizes the posterior under a Gaussian prior assumption on w, zero mean Gaussian prior assumption on w, and so the ridge regression solution corresponds to the map solution. So before we had the least square solution corresponds to the maximum likelihood solution. Now we have the ridge regression solution corresponds to the map solution.